Okay, everybody. Hello, my name is Steve Brewer. I'm a plant ecologist at the University of Mississippi. I've also done some statistical contracting work with DMR. And I want to talk to you about some methods for analyzing changes in species composition over time and its relevance to assessing ecological restoration success. So why is it important to analyze changes in species composition? Well, if we can agree on a reference conditions, that is, in terms of species composition, such that reference sites have the desired species composition. This could be species that are indicative of pre-disturbance, historical conditions, or maybe communities that contain rare and threatened species. We agree on that. And we have some degraded sites pictured here, then what we'd like to do is first see if when we're doing the restoration, we get to maybe a temporary stopping point. What is the similarity between restored sites and the reference? And is that similarity greater than with the unmanaged sites? Of course, another thing that we want to make sure of is that the restoration treatments that we've applied actually are making a difference. They're actually effective. And so that means we need to be able to quantify changes in species composition and look for convergence as a result, and changes that occur in the restored treatments, but not in the unmanaged treatments. You could get a situation like this where the restored or the sites that are being subjected to management are actually getting more similar to the reference, but maybe so are the unmanaged sites, in which case you may have kind of no need for restoration. The passive restoration or succession will ultimately result in the recovery of this community in terms of species composition. So statistical analysis of change, when we do it, we are often doing a repeated measures analysis. This can be done as a traditional repeated measures ANOVA or as a linear mixed model, where our sites or plots are considered random effects. When we do a repeated measures analysis, we look at between subjects effects and within subjects effects. And the between subjects effects, what we're doing here is that we're averaging the treatment effects over time. But within subject effects, which I'm going to make an argument today are much more interesting and informative, we're looking at the time effect itself and how the treatment effects on changes in responses occur over time. Restoration treatments are applied to treat degraded sites randomly, ideally randomly and independently. These sites then are considered independent observations, but the repeated measures over time at a given site are not independent observations, and our statistics need to reflect that. So when we analyze changes in species composition, generally what we need to do is use multivariate statistics, but that presents some challenges. We often have lots of zero abundances that make traditional multivariate methods such as MANOVA untenable. So the preference generally is for using methods based on non-Euclidean distances. And what I mean by a distance is kind of the dissimilarity in composition between any two observations. And one that's often used that deals with zero values pretty well is the Bray-Curtis distance or dissimilarity. And methods that can use that include permutation MANOVA, which is similar to traditional MANOVA, except it's based on distances, not on responses per se, and it uses a permutation test to get p-values. And then I'm going to argue that distance-based redundancy analysis can potentially be a good sort of complement to permutation MANOVA. However, repeated measures per MANOVA and DBRDA are not straightforward analyses, and they present some challenges. First, Permutation and MANOVA alone will not tell you which species are driving the compositional changes. It must be combined perhaps with an ordination method, and I'll argue DBRDA will be a good companion ordination method to actually determine which species are really involved in illustrating the treatment effects. Between subjects effects cannot be analyzed by simply averaging each species abundance among years. We can do this with a regular univariate repeated measures, but when we're trying to do this where the response, if you will, is actually a non-Euclidean distance matrix, then you can't do that, okay? And so as a result, the interpretation of between subjects effects is not straightforward. This is because the analysis to do it right is run on a principal coordinates analysis axis scores. So you're actually pretending like the axes are actually the species. And so you can look at how axes affect the results, but not directly how species do. Also, and this applies to just any kind of repeated measures that where we're really interested in the change in species composition, the main effect of treatment, that is the effect average over years, is misleading if the effect of treatments on species composition varies between years. For these reasons, I recommend running separate PERMANOVAs and DBRDA ordinations for each year, but also run these analyses on changes in the species composition. I keep mentioning it. What is distance space redundancy analysis, or DBRDA? It's a type of constrained ordination. A non-metric multidimensional scaling is an unconstrained ordination. Canonical correspondence analysis is one that's constrained by predictors, okay? I think it is the most appropriate companion ordination technique you could run to determine which species are driving treatment-related effects on composition that are revealed by the results of the PERMANOVA. And what it does is it generates species scores, which PERMANOVA does not, which can indicate which species are driving the treatment-related effects on composition. So to illustrate these concepts, I'm going to use some data from an experiment that I've been doing since 2014. It was established at wet pine savannas in this region of Mississippi, in 2 different areas. Neither site has been burned since 2012. And I set up actually 20 40-meter square plots, but I'm going to talk about 10 of them because 10 of them were subjected to annual clipping from between 2014 and 2019. So I'll consider each of these 4-meter square areas that were clipped annually as the blocks. And then within the blocks, I assigned 4 different treatments that basically corresponded to either a reference condition, which was basically just simply taking a 25 by 25 centimeter sod, digging it up and placing it back in the hole that I dug. That's kind of my reference. And then I did that with another one too. But then for the other 2 treatment plots, what I did is I transplanted 25 by 25 centimeter sods into these blocks, okay? And so those represent transplant treatments. And then I clipped everything, this is in the fall of 2019, and waited a month and came back. And then I treated half of the plots in a factorial arrangement with a herbicide, okay? And the idea, and I took censuses of species composition in both 2020 and 2021. And the idea here is to get an idea of how quickly can you get a composition that's similar to a frequently burned site from one where you're starting that has not been burned in a long time. And that was that kind of that transplant effect. And then the herbicide treatment was a way of kind of, determining, what are some of the mechanisms? How important is recruitment from a seed bank, or just simply recruitment of bare ground and recovery? Okay, our code, I'll present some of that for doing these analyses. What you want to do, what I did is I read in this species data file and a factors data for just the 2020 data, okay? And then I used the Adonis function in the vegan package of R to run permutation MANOVA. Here's an example of the code. It's your species in response to the block and the herbicide transplant and their interaction, okay? And this is what you get when you run that, what I got when I ran it. And you can see the block is significant, herbicide is highly significant, transplant is significant, and the herbicide by transplant interaction is significant. But the thing is per MANOVA, all it does is just tell you that these are significant. It doesn't really tell you why. It doesn't tell you which species were kind of driving those effects. And for that, you want to use, I prefer to use distance-based redundancy analysis. So I'm doing this on the 2020 data first. And just to, as an example, I'm just going to look at one factor, but you can do this for all the factors, for both factors and the interaction, in fact. And here what you have to do is it's going to be the species data. It should be a squiggly line, I'm afraid. Herbicide. And then you use this condition argument to factor out the effects of both the block and the transplant effects and their interaction. Now, when you use CAP scale, you can't actually, it won't let you enter in these interactions like this. So you pretty much have to make a variable that is a interaction variable. And since with the herbicide contrast, okay, herbicide versus non-herbicide, you have two levels of a single factor that you're looking at, and therefore you'll only get one dBA-RD axis. So instead of trying to plot a two-dimensional ordination, I just present it as a bar graph. And this top graph, what it's basically showing you here is that it's just kind of verifying that there was a significant effect, main effect of herbicide treatment in 2020. But these bars down here tell you they correspond to the species scores. And so this is the information that tells you which species are driving these differences. And as you can see, Dicanthelium encephalium, Rhynchospora of several species, and Drosera capillaris, the pink sundew, are really driving these differences, and you can or contributing to these differences. And what you're seeing is that they were associated with the non-herbicide plot. So that tells you basically, at least in part, it tells you that they were killed by the herbicide. Note that Lothiola americana, golden crest, actually was more associated with the herbicide plots. And I think that's partly an artifact. I think that's partly the fact that it just didn't get killed by the herbicide. And also it may have spread clonally into some of these plots from the adjacent areas. Okay, now we want to look at the within plot effects. And this is getting at the change in species composition, okay? And so here we read in the full data set, not just the 2020 data, but both years. We use the Adana function in vegan to run the within plots per MANOVA, making sure to include, this is very important, okay? Make sure to include a variable that accounts for the between plots variation, okay? And the model may look something like this. Species data for both years as a function of between plots variation, the year by herbicide interaction, the year by transplant interaction, and the three-way interaction. And when you do that, you get something that looks like this. First thing to point out is just ignore the between plots test. It's not really a valid test. It's just in there to remove the variation, the between subjects or the between plots variation from the error term, so that you're getting just you can just look at these within subjects factors. And here we see that year is significant. Year by herbicide is highly significant also. And the year by transplant is significant, but the three-way interaction is not, okay? And if we want to then look at which species are driving it, we use the DBRDA. Once again, you want to read in that full data set within plot factors. You want to add variables that will specify these year by treatment interactions and use the cap scale function to do this. And so a model statement may look like this: species data both years. Notice that here I've made a variable that represents the herbicide by year interaction. And then the condition argument is accounting for between plots, year by transplant and year by that transplant by herbicide interaction, and use the Bragg-Curtis distance. And this is just a reminder of the results we got from 2020. But now what we're looking at here is the change in composition from 2020 to 2021. And here what you see is, again, this is showing that there's a highly significant herbicide by year interaction, the change by herbicide interaction, if you will. And then when you look at the species here, notice that several of the species that were largely not very abundant in the control plots in 2020 are now more associated with having increased in these herbicide plots. Some of that is just coming up from a seed bank. Some of it is also that they may not be recruiting very well in the regrown control plots that recovered rapidly from the clipping. Okay. Then finally, we want to check for similarity of species composition. Here we can use PerManOVA to analyze the 2021 data and interpret results by using the DBRDA of the 2021 data. And this is what we get with the PerManOVA. We see now that block and only herbicide is the only factor that's statistically significant. And then we can show this in an ordination where we put in all the treatments, but you can see that what's going on here is the herbicide plots are separating out from the non-herbicide plots in 2021. And the species that are associated with those non-herbicide plots are such, the Rhynchospora, Dicanthelium, toothache grass, Tinium aromaticum, Muhlenbergia, Galisacea, and then Lophiola americana, Drosera capillaris, Pseudolycopodiella caroliniana, and club moss. They're associated with the herbicide plots. So the herbicide plots have not become more similar or significantly more, similar to these non-herbicide plots. So some recommendations, summarizing the results: analysis of changes in species composition is important for evaluating restoration success. We want to look at similarity between treated and reference sites, evidence of significant change in composition as a result of our treatments. We want to analyze species composition using multivariate statistics, and we may need to deal with some of the limitations and challenges of multivariate statistics. We want to probably use these these distance-based methods, and just remember that repeated measures PerManOVA, when we're looking at Bragg-Curtis distances, are not straightforward analyses. The between subjects tests are cumbersome and difficult to interpret. So I think doing separate tests for each year while also doing tests of the effects of the treatments on changes in composition between years is much easier to interpret. And with that, I'll stop and I'll take questions.